I would say in numerical methods in general, and the finite element method specifically, has been one reason why we have been able to achieve this type of progress in a relatively short period of time. I mean, thinking probably 200, 300, or probably 500 years ago up to probably 100 years ago or 100 years ago, we have not been able to achieve this amount of progress in few centuries, let alone few decades. So the reason is this processing power we have, this computing power we have, that has enabled us. And the finite element method, I would say, is probably arguably is one of the strongest tools you have as an engineer who's graduating in the 21st century. Now, numerical methods has been there for ages. They have been used by ancient civilizations in Mesopotamia, in China, in Greece. They have developed different type of numerical methods, but they haven't been able to achieve huge progress using these numerical methods because they relied always on numerical calculations done by hand. But we have computing powers that can process a huge amount of computations compared to anything we had as a human being in the past. Now, I want to talk about a very specific example. This is quite a relevant example if you think about it, is the energy example. And I'm going to compare fusion to fission. So the fission power, we understood it, and we had an example or an application for that in 1945. This is unfortunately the atomic bomb. But by 1945, we have a full understanding of the fission, how it works, how to harvest the energy coming from fission. And we produced a bomb we have used in 1945. Compared to that, we understood the fusion power quite well, and we understood how it works, and we developed an application for that as well. This is the fusion bomb, which has been tested in 1952. Now, this is 7 years behind the fission power. Now, if you look into the applications, commercial application, and using nuclear power, fission power to produce energy, you can see that the first nuclear power station, which was connected to electricity grid, was put in work in 1954, whereas we still have not achieved anything commercial with fusion power. Now, so this is a lot of time without being able to progress. Now, what is the difference between fission and fusion? When you do the fission, so this is the nuclear reactor, you have nuclear waste, you have radioactive materials, and it is impossible to control the reaction once it gets outside the control. Once you lose control on the nuclear reaction, you cannot control it. It's going to blow up, and the reaction is going to continue, and it's going to become an international disaster. Whereas if we're talking about the fusion, we don't have any radioactive material. We basically use water to produce energy, and it is an infinite amount of green energy. We don't have any radioactive materials. If the reaction is not, if we lose control of the reaction is going to stop, and it's not going to be sustained by its own self. So once a disaster would happen in a fusion reactor, what is going to happen is the reaction is going to stop, and the problem is going to be very local. It's not going to spread on the international level like what could have happened in a nuclear reaction if we're talking about a nuclear power plant. Now, do you have an idea why we have not been able to progress on the fusion side compared to the fission side? Any idea, anyone? I mean, think about it. In order to start the fusion reaction, we need to increase the temperature up to 100 million degrees Kelvin, 100 to 150. I mean, in reality, we need to increase it up to 1 billion degrees Kelvin, but this can still be achieved at 100 million. Now, 100 million degrees, this is 10 times hotter than the core of the sun. I mean, you need to create on Earth something that is 10 times hotter than the core of the sun. I mean, the sun can't sustain this type of reaction because the pressure at the core is very high. Compared to that, we cannot achieve anything close to this on Earth. So we need to increase the temperature tenfold to the core of the sun. Now, you have something that is 100 million degrees, 100 million degrees Kelvin hot. You want to contain this on Earth within some material. Now, there is no material that we are aware of that can contain or create a confinement for this type of plasma once you heat it to 100 million degrees. And on top of that, you need to keep this plasma moving. So the solution for this is you cannot contain it within a material, so you can create an electromagnetic confinement, and you contain it within this electromagnetic confinement. And in order for this to keep moving, you create a donut shape. Now, this sort of designs are well known since the 50s, but we have not been able to work on them because they are quite complex. Now, I'm going to tell you about some project that started to look into both applications. So the first one is the tokamak, and the second one is the stellator. Now, the difference between the both designs, the tokamak one is the Soviet design, and the stellator is the American design. The tokamak one is relatively simpler to build, but it is a lot more complex to operate. The stellator, on the other hand, is very complex to build, but once it is working, it is a lot easier to process. Now, different nations are betting on different designs, so you can see that projects trying to exploit the tokamak are happening in the UK, USA, France, and China. In the UK, we have different examples for the tokamak. It's different projects working on that. Whereas for the stellator, the main projects are happening in Japan and also in Germany. I'm going to talk about specific design. This is the Wendelstein 7X, because if I want to bet my money, I'd probably go for the stellator rather than the tokamak. Now, if you look into all these projects started sometime in the late 90s, early 90s, and they have been possible. I mean, these initial designs have been possible because we have numerical methods such as the finite element method. Basically, the finite element method was used in the stellator design. And this is quite a complex design because think about it. You need to control atoms, or once we talk about plasma, we are talking about a cloud of electrons and neutrons floating around. You want to control them. You need to control their path, and you need to control it in a specific way so that they keep rotating. Now, if they rotate in a donut shape, they are going to basically segregate because some of them are going to have a shorter path than the other ones. So this is why we need to rotate them in the diagonal direction as well. So the tokamak will rotate the magnetic field itself to keep particles moving, whereas the stellator will basically rotate the donut shape itself. Now think about that. So to create a design that can work on this sort of scale, we're talking about electron and neutron scales. So this type of scale is really very complex to optimize, and this has been the reason why this has been delayed so far. Now, I'm quite optimistic that we are going to achieve something probably within the next 20, 30 years, but we are getting something that started to work. I'm going to talk, as I said, about the Wendelstein project. This is a German one. It is being worked at, or it's being worked on in Max Planck Institute for Plasma Physics. And I'm going to talk about the time scale this project has been working on. That's the planning. The initial planning was initiated in 1980, got European funding in 1996. The assembly began in 2005, and then they started the project in 2014. We had a working stellator. Now, in the first operation phase, in phase 1, in 2015, we have been able to create a helium plasma. This is 1 million degrees Kelvin. It's still not 100, but 1 million is already quite hot. And the plasma has been sustained within the stellator for 0.1 second. In 2016, the temperature has been possible to increase to 10 million Kelvin for the helium plasma. And 2018, this went up to 40 million Kelvin. And the plasma has been sustained for 0 to 0.2 seconds. So this is quite a big project. In 2018, they stopped phase 1 and they have moved into phase 2. Phase 2 is planning to start in 2022, and then we're talking about 100 million degrees Kelvin, and they are going to sustain this reaction for a bit more time. Now, just like one of the comments you mentioned, the reaction is not quite economical in phase 1 because the amount of energy you need to put into the plasma is less than the amount of the energy you get from the fusion reaction. But once we get into phase 2, in phase 2 is going to be probably more economic, but it's still experimental sort of thing. Now, Nature Physics and the Wendelstein project has made it to the cover of Nature Physics, which is probably one of the most reputable academic or a scientific publication. Now, as I said, the design has been quite a complex one, and it was only possible because of the finite element method. Now, the finite element method has enabled doing things which we couldn't have done many years ago, not many years ago, 50 or 60 years ago, and it has created a space for us to work on things that we could have otherwise only worked on using our imagination and a piece of paper. Now think about it, you have a window on a virtual reality world where you can test ideas, build ideas, and experiment with them, optimize them. Once you get into something quite optimum, then you get into the reality and you build it. You don't need to waste a lot of time and a lot of resources experimenting on things. So this is the power of the finite element method. I'm going to show you some examples which we have in the method. Sorry. All right, so this is an impact load. You can design a structure to take an impact for something you cannot never experiment with. We can work with particles if we're talking about discrete elements. If we talk about discrete elements, you can work with parts rather than a continuous material. We talk about high plasticity levels and plasticity based on different assumptions. Again, we talk about very large plasticity and deformations to a scale that we have not been able to work with in the past. Think about contact problems, for example. Designing contact problems is quite complex if you are going to work on traditional methods. Again, we're talking a highly nonlinear problem here. This is elastic, but highly nonlinear. An impact load where you have partial penetration or full penetration. Again, this is a fluid dynamic problem where you have a contact happening at the joint, where at the same time you have a computational fluid dynamics happening at the same time. So this is again a highly nonlinear polymer that you want to optimize the design so that you can minimize the stresses or the possibility of rupture. This is a coupling between heat and stress. So you basically have a very hot material, you are bending this material, and you have resulting stresses. The stresses will change with the temperature because the material property will change with the temperature. This is an example of welding and cutting. So this is an example from fracture mechanics. And this is again coupling between heat, pressure, and the stress. This is an example for welding and the stresses resulting from welding. So the heat would result into stresses. This welding point is moving, and you can understand the sort of stresses with the results from this process. This is another example from sport engineering. So as you can see, it's just an infinite number of examples. Now, the software has been used to produce this example. It is called Nastran, but you have many other softwares. Now, the finite element method is very popular not only for structural engineers, structural and civil engineers. It's also very popular for electrical engineering, for aeronautical engineering, mechanical engineering. So it's pretty much in any discipline of engineering, they are using the finite element method. So basically, if you master the method, you can work in pretty much any one of these disciplines because it is still the same method. And there's a large number of softwares that are available to work with this method. You probably have heard of some of them. You have ANSYS, Abacus, LS Lusas, LS Diana, Lusas, Nastron, the one we have seen examples for, is just a large number of software. In this course, I'm not going to focus on one software. I'm going to use Lusas in this course as an example for the concepts that we learned the theory about. But you are free to learn any software of your choice. And for the coursework we are going to basically work on later in the semester, you can choose any software you want. Now, I've picked Lusas because Lusas has probably the most easy user interface, but feel free to learn any other software. As I said, the purpose of this course is not to learn a commercial software. The purpose of this course is to learn the finite element method. And once you master the method, you basically can move from any software to another one quite easily because you basically understand the theory of it. So this is a list of references about the method. I think this is the list of, well, this is a list of the most important books, I would say, on the method. And if you want to think about a Bible on the finite element method, each one of these books will probably make a Bible. My personal favorite is the Finite Element Procedure in Engineering Analysis by Bathy. He's in MIT, but any one of these books are also quite good. So this is a list of some books that are available in the library as well. I would suggest, if you are interested in the method, to try and find resources yourself and read about it yourself. I mean, the finite element method is a rather complex method. I'm going to try and explain the basics of it, but you can develop your knowledge in quite some extra space if you want, or if you are interested in. 4 main units. I've prepared the printout for each unit. I've left, I mean, the handouts, the printouts are basically similar to the presentation itself, but I've left some empty parts in them so that you can try and fill the gaps as you are working on this course. Now, the gaps will tell you exactly what part you really need to work on compared to other parts that you can't read. So it is important that you work on things yourself. This is quite important because if you don't work on this, it's not going to be easy to understand the method. I'm not going to say that the method is easy, but I'm going to simplify it the best I can. And we start from quite a simple situation where you build up your knowledge up to quite an advanced problem, as you see by the end of this course. But it is important that you work on the material as we progress through the material, because otherwise it's going to be quite a complex idea that you are working on toward the end. And to work on complex ideas, you really need to build up your knowledge and take your time while you're building the knowledge. It doesn't work. I mean, the finite element course is not the sort of course that you come just before the exam and understand all of it. You need to build your knowledge step by step and give yourself enough time to digest the knowledge. All right, so the handouts are designed to help you by basically identifying parts that you need to work on. And I'm going to put these handouts, these copies of the presentation, basically where parts are omitted, I'm going to put that on Canvas. And after the end of each lecture, I'm going to put a full lecture note. So basically the missing parts are available in the lecture notes. The lecture notes would include all the material I've been discussing in the class. And this would also cover the parts that are left empty in the presentation. So if you want to find the full thing, you find it in the lecture notes. If you want to work on the course, I would suggest that you work on the handouts. All right, now the handouts, I mean, I originally designed the handouts to be happening in the class itself. So you would be, I would hand out these presentations with the empty parts omitted from the presentation. And I would ask students to take notes, trying to fill out these empty sections. But obviously they can also take their own notes. This is completely up to the students. But as I said, the handouts are kind of designed to help you structure your knowledge of this course. Now, since this is going to be online this year again, So I'm thinking probably you can print out the handouts if you want and go through them as we work on the material, but also if you want to take your own notes, this is absolutely up to you. The material I'm going to cover in this course is going to start from the very basic of the finite element method. We are going to create the simplest possible element that I'll probably just tell you a little bit about the method before we get into the structure of the course, so you see how this will fit into the context. The fundamental concept of the method is to find a problem that you have, or you have a problem that you want to solve. The problem is really complex. For example, in biomechanics or in bioengineering, you want to really understand the stresses applied on a skull based on certain forces, certain boundary conditions, certain implants, certain internal pressure inside the skull. You want really to understand that. You cannot do this with the standard methods you have learned in structural engineering, but you can do this using the finite element method. Now, how you do that is you have the complex problem, you divide it into simple problems. So the geometry of the skull is very complex. Instead of working on this complex geometry itself, you divide it into smaller parts. These smaller parts are very simple geometries. So for example, you divide the skull into 4 noded elements, where each element will resemble a rectangle, for example. And then these rectangles are very simple to solve compared to the skull, the original problem. Now, you design or you describe your problem on each one of these elements, on each one of these squares or rectangles, and then you assemble them, you solve the full assembly of these small problems, and you get the solution for the big problems. So you basically get the distribution of the stresses. If it is a dental implant, for example, what sort of stresses can happen in there, what sort of accidents. I mean, an example, for example, if you have an impact on the jaw, what sort of stresses are going to result on the implant, and how the implant can affect the bones of the skull. There's just so many different applications in biomechanics and bioengineering to working on bones, for example. All right, so you have a complex problem, you split the complex problem into small problems, many of them. Obviously, you cannot do many small problems by hand, but a computer can do that, and the computer will solve these many small problems and produce the solution for the global problem. Okay, so this is how the method would work. I'm going to first of all explain the simplest possible element you can think of, which is basically the building block of the finite element method. And then we start from this simple, very simple element. We are going to discuss different concepts related to the finite element method, how they are implemented on this very simple element. We are going to discuss things in the relation between the stresses and the strains, how to move this, how to map this element into any variation of elements. And then we are going to move into quadratic line elements. We start from a simple one-dimensional linear element. We move into a simple one-dimensional quadratic line element, which is one step higher, one level higher. And then we describe applications of that, how they would become relevant to a two-dimensional problem, and what sort of changes we need to make in order to get into the two-dimensional problem. And finally, once you understand, it's basically you have a very simple element, you understand how it works, we make it more complex by improving the order of the approximation. We're still talking about a simple element, but better approximation. And then we move from 1 dimensions to 2 dimensions. And if you understand how to move from 1 dimension to 2 dimension, you would basically apply the same concepts and move from 2 dimensions to 3 dimensions. So this is basically how it works. And then we are going to talk about the designing process using the finite element method. So once you understand the background of the method, once you understand how it works, then we can talk about applications and how you can use it in real world applications. And to an extent, this is going to be covered also in the coursework. So in the coursework, you are going to basically implement all the theory we learn. We are going to implement it in a finite element software package. Now, the finite element is not designed to be done by hand, so you don't do it using hand calculations, obviously. It's not designed for that. is designed to be implemented on a computer, but to understand the theory of it, you need to solve some problems by hand. This is no way to avoid. You need to solve some problems by hand, you understand the theory, and then you move into the software and you work on it. Now, as you can see here, the software can produce a lot of convincing results, but you never know if these results are correct or not unless you understand the theory and the background of the method. Now, if you don't understand it, it's very easy to produce a lot of rubbish using the software, and you believe the rubbish and you go on and design according to the rubbish you have produced, whereas in reality, this is going to mount to nothing. It's basically your design is completely flawed. It's not going to work. All right. So it is very important before you get yourself into using this software, really complex software and very complex results and very complex problem you are going to work on is very dangerous if you don't understand the theory behind it. I hope you can see that.